Back to my channel. So today we shall be looking at this question that's a range sum of BST. So it's a given the root node of a binary search tree. So you know what a binary search tree is. It means all the nodes to the left of the root, they are less or equals, and all the nodes to the right are greater. So, and it is binary because each node can have maximum of 2 children. So two integers low and high, return the sum of value of all nodes with a value in the inclusive range low I. Okay, what does that mean? So we're given this root. The low is 7 and the I is 15. So all the sum of all the value with a sum of all nodes with a value in the inclusive range. So we have 7, 10, 15 are in the range. So we had all of that. So here low is 6, I is 10. So the values in the range will be 6, 7, and 10. So the number of nodes in the tree is in this range. So we have at least one. So there is no null. The value maximum, the low minimum of 1, and maximum, and all the node values are unique. Well, how do we approach this problem? The way I can think about it is if we can use the notion of in-order transversal, and an in-order transversal can give us all the nodes in a sorted order. Then we can now just pick the summation of all the nodes from the value that we're looking from up to from low up to the high. So in-order transversal will give us 3, 5, 7, 10, 15, 18. So that will return that for us. Then once we have 3, 5, 7, then we can just fix 7, 10 plus 15. Here to in-order will return for us 1, 3, 5, 6, 7, 10, 13, 15, 18. So in order we return it sorted. So we can just do the addition. And that's the best way I can think about it. So we create a in-order transversal. Then we need to have like the nodes. So the space complexity will be big O of n because we need to have all the nodes kept. The time complexity will be big O of, we have to go through the entire one, the entire height. So I'll say big O of h, where h is the height of the tree. All right, so let's define an in-order function. So this is in-order function. So it takes a node, and that in-order nodes we recursively call the in-order. To recursively call the in-order with node dot left. Then we call the in-order again with node. Okay, since it's in order, so in between this and this we have to now have like a list that takes the nodes, and we just append the node to that list. So we want to like take okay, so we want to carry that list around, so that when we call the list at the end of the day, this is going to return the nodes. So then we want to call our in order with the root and an empty list. So at the end, we can now traverse through the nodes, and for node in nodes, and we want to declare our total to be plus equals to the node, but only if the node is within the range. So our total is equal to 0. So only if the node is within the range. So we need to do some modification on that. So at the end we return our total. But we need to check this, what we're adding, and make sure it's within our range of values with low and high. So we'll check and say if this one should be val, because we are adding the value. So we just check if node.val, if it is greater than or equals to the low, or it is, should it be or? No. And, it should be and node.val is less than or equals to the high, then we want to add it. But I think that should be it. All right, so let's check and see what we have done. So this is our root. Recursion is difficult to oh, so now here we've not handled the base case. So our in order is not yet correct. The base case will be if not node. So if it does not exist, so that it can terminate, we return. It just returns. Yeah. But yeah. Now, but there's something here. So here we're returning none, and here we're returning nodes. Does that actually make sense? Is it not possible for us just to append this? Because we just need the same copy. So we have the nodes outside declared. We expect that it will be available inside this function. So I would think the best way for us to declare nodes outside this way, so we don't need to pass in into this anymore. So we just have one copy, and here we don't need to return any node. So we're just modifying that. And so we're just calling this one and we're just appending that node. I think this is better. Yeah. So when we now call the in order, we call it with just only the root. So it will populate these nodes for us. Okay. So let's see. So our nodes is empty. So we get to this place. Our root is 10. So if not node, that does not apply. Then our root becomes 5. So our node becomes 5 here. Then we recursively call this. Okay. If not, that does not apply. So the left becomes 3. So if not, that does not apply. Then our nodes of left becomes none. If not, oh, so that applies. So we previously had 3 on the stack, so it appends that 3. So this becomes has 3 in. Then it comes to the right. Okay. So recursion is difficult to explain. So node dot right. So what is our right now? Yeah. So it comes to the right of these 3. So we're in 3 now. So we've append 3. We've gotten the none. So it comes to the right, so there's none. So you backtrack right. Then we get back to, what should we get back to now? I think we should get back to 5. Well, this is difficult to really explain, but our logic should be clear that we keep going to the left, left, left until we pick this. Then we see no left, we pick this, then we go to the right, and we have that. Okay, let's run it and see what we have. Good, so that's correct. All right, so let's see another one. In this case, it's 6 and 10. Okay, let's see that too. Good, that's correct too. So let's see all of that. Good, so that's correct. So the real thing we're trying to get here is the in order. The in order transversal will give us the sorted binaries, the sorted nodes of the binary search tree. So that's the key important thing here. That is remembering this in order, and we did it within time. But my apology, it's difficult to actually trace out this recursion. You may want to use something like a Python tutor to see how this recursion actually works. Okay, but that's what in order is. In order because this is in, and it automatically just sorts a binary search tree because all the nodes on the left are less or equals and all the nodes on the right are greater. So when you use in order, it will come with a sorted version, which is from the lower 3, 5, 7, 10, 15, 18. And here it will be 1, 3, 5, 6 to pick 6 for 7, then 10, 13 first, 15, 18. That's just the property of in order for a binary search tree. All right, thank you very much, and see you in the next one.